Hi. Today we're gonna start discussing the second most important application of the Lagrange multiplier method in the economic context. And in this special case, we're gonna try to use Lagrange multiplier to figure out how much of capital and labor a given company should employ. Okay, so look, we're starting with some cost function for the company, where this is the total cost of production. And now, we can hire only two factors of production. One of them is labor, and one of them is capital. Now, these are the quantities of labor and capital used, but of course, before we pay for them, we need to know their prices, right? So this is going to be price of labor, and this is going to be price of capital. So in other words, we can think about it as wage, and about this one as rent. So here is how much costs, for example, 1 hour of work. How many hours of work are we using? Here is how much does it cost to rent capital for 1 hour, and this is how much we actually use. So this is a total cost function of the company we are considering. And of course, as this is the cost, our entire job is going to be to minimize. However, of course, if we wouldn't use any capital or any labor, we wouldn't have any cost, but we also wouldn't have any production, right? So this is something that we need to minimize, right? However, we need to impose some restriction on this function, because otherwise we should just stop producing whatsoever, right? Okay, so let's just say that the production function in this company is just some production function that we are not going to specify functionally. We're not going to write down its functional form. However, let's assume some very basic thing about it. So first, marginal product of capital should be higher than 0, which means that the more capital we use, the more we produce. However, the second derivative of level of production with respect to capital should be negative. So we have decreasing returns to factors, which means that if we keep the level of labor constant, then if we increase the amount of capital we've got in the company, we will be able to produce more, but each additional unit of capital will bring less and less additional production. And we make exactly the same assumptions about labor. So, given some level of capital in the company, we are expecting that if we hire more workers, we will be able to produce more, but each next consecutive worker hired will be bringing less and less additional production. Now, finally, there is one more derivative we can calculate here. This would be a cross derivative, right? So what if we would differentiate marginal product of capital with respect to labor, or marginal product of labor with respect to capital? And look, again, if we will get more capital into the company, we would expect that each worker would be more productive, right? And if we would hire more workers in the company, we could say that capital they have is going to be used more intensively and more effectively, right? so we expect for this derivative to be positive. Okay, so this is the production function that we have. However, look, this is a problem in which we are minimizing the cost, which means that we must set up some level of, some fixed level, target level of production. It can be the one dictated by the market in the perfect competition model, or it can be a result of an order the company received. Okay, so let's just say that this level, this fixed level, is Q0, right? So we got that we need to combine capital and labor in such a way that we're going to produce exactly Q0. And this is actually going to be our constraint, right? If this is our constraint, which says that only combinations of capital and labor that give you this exact amount of production, right? If this condition, if this restriction is fulfilled, we can say that 0 needs to be equal to Q0 minus Q K over L. And we're going to use this 0 when we're going to build Lagrange function. Okay, so Lagrange function is going to be first the function that we are minimizing plus lambda times 0, but of course 0 taken out of the restriction. Now, of course, we need to start with the first order condition. So we first differentiate the system with respect to the Lagrange function with respect to lambda. So we get the repetition of the constraint, and then out of the two next equations we get PL minus lambda QL equal to 0, and out of this we get that this is PK minus lambda QK equal to 0. And look, I can solve this equation for lambda, and I can solve this equation for lambda, right? So out of these two equations, I'm getting that lambda, let's say we solve this system of simultaneous equations and we've got equilibrium solutions. So our lambda is going to be equal to PL, right, out of this equation divided by QL. Or if we take it from this equation, it's going to be PK divided by QK. And look, this is our optimum condition. Of course, we need to check a little bit later whether the Hessian, border Hessian we're going to get here is definitely negative, because of course we want a minimum. However, look, we're going to express this result a little bit differently. Look, what I'm going to do is I'm going to divide both sides by PK and multiply by QL. So we will have PL over PK, and this is going to be QL over QK. Right, and then the one last thing I'm going to do is I'm going to put minuses over here. Multiply both sides by -1. And now look, as it turns out, this condition states something that is actually very, very similar to what we had in the case of the budget customer's budget problem, right? And we see that this is looking very similar to what we had before, also associated with budget line, right? And this part is somehow associated with an indifference curve. Okay, so definitely there is some translation over here. Okay, but let's do those things step by step. So look, we out of the equation for cost, we can actually calculate a cost line. A very specific cost line that I'm gonna explain in a second. Look, so we've got that C equals PL times L plus PK times T. Let me solve this for K, okay? So we get that the PK is equal to negative PL times L plus C, or K is equal to negative PL over PK times L plus C over PK. Okay, and look, this is a linear equation, right? This is its coefficient in labor capital space, or we could also say that the slope of the cost line is equal to this, right? If we calculate derivative, this is what we would get. Okay, let's put this line, now that we have it, let's put this line on the graph. Okay, so look, we can actually figure out also, we know that this is a straight line, right? It's a linear equation, of course, it's a straight line. Now, when we get in a very similar way, in exactly actually the same way as we did with customer's budget, we can clearly see here that if customer if the company would like to spend all the money on labor and hire labor alone, then we would have that C equals to PL times L, right? So dividing C by PL would give us the maximum amount of labor we can get if we spend all the money on it. Okay, so let's just say it's somewhere around here. So here we have some C over PL. And look, by the same token, if we would like to spend all the money on capital, all we need to do in order to find out how many units of capital we can get is to divide the cost by price of capital, right? Okay, so we get here. Okay, so we get the line by connecting those 2 points with the straight line. And now let's think what kind of cost this line represents. Look, the thing is that if we would choose any combination of capital and labor that lies on this line, we would have exactly the same cost of each of these combinations. This is why this is called an isocost. And what we see over here, what we got from the equilibrium condition, from the optimum condition, is that left-hand side of our equation is the slope of the isocost. Okay, now look, one thing that we are doing over here is that we are trying to get on the lowest possible isocost line, right? We are trying to be at the lowest possible isocost line because it means the lower the cost for the company and later, of course, higher the profits in the short run or maintaining its existence in the long run. So look, what we want to do with this isocost line is to move it as far down as possible. However, we know that we can't just go to zero. We need to produce a certain amount. We need to produce a certain amount of product, right? Without this, we will not make any money. So we need to now choose among every possible isocost line the lines over here, the one that will also give us the output that we want, and this cost will be the lowest. Okay, so how do we get this on our graph? Look, of course, the second part of the story that we see over here is associated with the production side, right? With the production function. And look, in the case of this production function, we do not know its specific form. However, we can always differentiate this equation to see the slope of the line that this production function is actually producing. So look, we are assuming that Q0 stays at a constant level, right? So we have some target Q0 that we need to meet. And what do we do next? We do very similar as we did in the customer's model. We calculate total differential of this expression. Because if we, of course, okay, so total differential of this expression is qk times dk plus ql times dl. And now, over here, if we are assuming that this is the target level, it will not change, right? So we will have differential that is equal to 0. Now, we can solve this quite easily for dk dl, right? We have qk dk equals negative ql dl, or dk dl is equal to negative ql qk. Okay, and now what we got over here is again a slope that is negative, but the slope of what? Look, generally when we calculated this differential, we are actually asking the question, what combinations of capital and labor will give us exactly this amount of production? So the line that gives us all those combinations is something we heard just recently is called isoquants. And this is the slope of the isoquant. This slope in microeconomics is usually called marginal rate of technical substitution. It simply measures the ease with which we can substitute one factor of production for the other. Okay, and look, it's simply given as ratio of marginal products with minus upfront. So look, now if I want to add isoquant over here. This isoquant will have shape similar to very similar or identical as indifference curve, right? So this is our isoquant. Okay. And now look, this isoquant is associated with level of production Q0, right? So what we get is that every combination of capital and labor on this graph is, on this line, is giving us exactly the same amount of production Q0 out of this production function. Okay, so now that we know what each side of the equilibrium condition, optimum condition says, we also know what we need to do here. We need to find a point at which the two lines have the same slope, or simply tangent to one another. And look, when we were using customers, when we were doing customers problem, our goal was to take the indifference curve and move it slightly higher, and higher, until we end up at the point of tangents, right? We were maximizing utility given restrictions on that budget. However, now we're doing a different scenario. Look, first we look for a minimum, right? So we want to make the cost as small as possible. So we are going to be trying to move cost downward. And in this context, of course, the level of production that we want to achieve is given. So this stays and does not move. In other words, we would be trying different isocost line. Of course, remember that they are 100% straight. They are not curvy, but I'm not a rocket, right? Until we would get to the one that has only one tangency point, with that isoquant. And look, we can be sure that over here, let's name it C1, this is going to be C0, C0, C1 over PL. Here, we've got the lowest cost that is going to give us the level of production associated with this indifference curve, so isoquant, so Q0. And of course, at the intercept, we're going to get the level of labor and the level of capital that the company should hire. Okay, so graphical analysis is already telling us quite a lot, and it's showing us that this is rather a maximum. However, we need to take into consideration one more thing. Well, we need to take into consideration that we still haven't proven that this is actually a minimum, right? So this is going to be our next step. We're going to use second order condition, and with second order condition, we're going to establish whether order Hessian is positive or negative. However, when we're going to be doing so, we're going to encounter lambda. And we need to think about the sign and interpretation of lambda here. Look, in the customer's choice problem, lambda was marginal cost of money, because lambda represents comparative static derivative of z with respect to budget constraint in our to the constant in the budget constraint. Like in our case, this is simply cost of production, right? I'm sorry, Q, 0. So here we get what would happen to the optimal level of cost, so to the minimal level of cost, assuming this restriction is binding, if we increase target production by 1 unit. So this is cost of optimal production, increasing production by 1 unit. And look, so what we get out of it is that lambda is constant, is positive, because we expect this cost always to be positive, because when you produce something, you always need to use some resources. However, we can also get it from here, because look, what I could do here is I could, just like we did here, so we get that PL over PK is equal to lambda, right? So we know the ratio of two prices that are positive must be positive, so we know that lambda is positive. Okay, I needed to speak about it a little bit because it's very crucial in our next step. So what we're going to do now is to calculate the border Hessian and see if it has a positive or negative sign. So the border Hessian, here it is. First, we differentiate this equation with respect to first lambda, k, and l. And of course, because this is border Hessian, we know that we will have the same over here. Then over here, we've got negative lambda QLL, and here negative lambda Q. I'm going to write it as QKL, right? And I'm going to do the same thing because I know it's here, it needs to be here. And finally, over here, we're going to have negative lambda QKK. Okay. So now, unfortunately, we need to calculate it all out. One thing we can do is I can take out negative 1 of the first column and of the first row. It's going to cancel each other out. So I can write it like this. Okay? And the next thing is to just calculate. So this is 0. Here we've got QK times QL times negative QKL, right? But this is the same as we were going to get if we multiply this times this and this. So first component we're going to get over here is negative 2 lambda QKL QL QK. Okay. Then what else? Then we can calculate going upwards. So we have QLL times QLL times negative lambda QLL, and with minus in front, so it's going to be plus. So we've got lambda times QLL times QL squared. And similarly, from this line, because this is of course 0, from this line we're going to get plus lambda QK K QK squared. Okay, and look, we right away see that lambda is in all the expressions, so let's take it out of the parentheses. Okay, now all we need to do is to assess the sign of the expression. So what we know? We know that expressions in squares are positive. We also know that lambda is positive. We just discussed this. And what else do we know? We know that when we increase level of production, and when we increase level of capital or labor, production increases, right? We get that this and this is positive. However, we know that we've got decreasing returns to factors, so second derivatives with respect to the same variable are negative. And finally, we know that having more capital increases the productivity of labor, so this is positive as well. And look, what we get out of this is that this expression here is negative. This expression here, alongside with the minus, is also negative. And finally, this expression here, negative. So we've got a sum of three negative terms multiplied by positive terms, it remains negative. And because this expression is in fact smaller than 0, we can be 100% sure that we find a minimum. Okay, so we know how the company should choose capital and labor. And we also know what is an isoquant and isocost. In the next couple of videos, we're gonna elaborate on different types of production functions and that they're associated with different types of isoquants and isoquants. However, next thing we're gonna do is we're gonna see what is actually happening when companies' budget and cost is increasing along the side of the increase in the target level of production. Okay, thank you for your attention and see you in the next